or university, and he is the leader who has played pivotal roles in advancing education and research. The hybrid nature of this conference, blending physical and virtual participation, reflects our commitment to inclusivity and the adaptation of innovation solutions. It has followed to bridge geographical gaps and create a truly global platform for intellectual exchange. To the organizing committee, whose tireless efforts ensured the seamless execution of this event, I extend my heartfelt appreciation. Your dedication, meticulous planning, and attention to detail have been instrumental in making this conference a resounding success. In conclusion, as we draw the curtains on this chapter, let's carry forward. As we step into the future, let's continue to foster international collaborations, embrace diversity, and champion of the pursuit of knowledge in all its forms. Thank you to everyone who has contributed to the success of this second international conference on recent advances in mathematics forum 2023. Thank you very much.
Thank you very much, sir, for your detailed report. We'll sum up all this.
In the International Research Conference on Applied Computational and Pure Mathematics. This event has been a celebration of knowledge, collaboration, and the global spirit of the academic inquiry. Over the past 2 days, we had the privilege of hosting more than 100, including 20 invited speakers, 20 keynote, 30 invited speakers, and there were some speakers who were here physically from abroad. There were 5 people who were here, and the presenters present their presentations here. The distinguished scholars from various corners of the world, including Turkey, Malaysia, Iran, Iraq, UAE, almost from the 70 different countries. Their insights have also sown the seeds for future collaborations that transcend borders. Our gratitude extends to the more than 1,353 participants who actively engage in discussion, presentations, and networking sessions. There is only one session is here at the moment, but there are
which is the continuous variation of physical layer as weak star topology. More precisely, if we have a system of family of dynamical systems, then a map in that system is called statistically stable if the function which associates maps to the corresponding physical layer is continuous. Here, in the space of probability measure, we consider the big star topology. Thanks to Rees, Markov, the dual of the continuous functions are by Rees, Markov are identified with the space of regular measures, and the unit ball is just the probability measure. So we can consider big star topology in the space of measures. And if the densities of measures exist, then we refer the strong statistical stability, continuous variation of the densities of physical measures. So densities we can take as an integrable function, so we can take L1 norm. Especially in the case of SRB measures, as they are absolutely continuous, again by the by the radar Nicotian, we have densities, so we can take the strong statistical stability in the case of SRB measures. So we start with a simple example of quadratic maps. There seems to be very simple one is X shared one.
This linear comes from the state to the monopoly. It satisfies the following condition. This foundation, this linear comes from the shifted the theorem of those sequences for each sequences. So it looks like this one. We dx and shifted the x and plus lambda. Usually we use the set of all the Banach limits on an infinity. If the boundary sequences is safe to the Confluence conversion, if all Banach limits this coincide. So the C hat usually denotes the space of the Confluence conversion sequences. Now, again, every conversion sequences is Confluence convergent. But usually the converse is not true. For example, if you consider the sequences 1, 0, 1, 0, 1, 0, 1, 0, this sequence is not convergent, but this one is convergent, 1 over 2. So, this is the more general than that. So, just I explained already, but for the convergent sequences, all the Banach limit coincide. But there is a problem. What about the boundary sequences? So Banach defined that kind, Banach limited to show that all the Banach limits will coincide for the boundary sequences. So for example, if we took this one and we pose it from the linear one, along with 2, this is. So if you consider the x, this one, so it should be the x plus the x. So it should be the one term is shifted, so this is 0, 1, 0, 1. If you add to this one, LE, we know that this is the 1, so this is equal to 1 over the 2. So this sequence is not in conversion, but Confluence conversion. So this is a very important concept for the functional analysis. Later on, after the Banach, Lawrence also studied this concept and defined this one. For the boundary sequences, the limit exists and uniformly in M. And with T, M, and X, this one. And we shifted the terms, and this one looks like this. So all the strong Confluence conversion sequences was introduced by the Maddox, the British mathematician. He was about the summability theory and the sequence spaces. And he published about the elements of function analysis. This book is very important for the function analysis and the summability theory. And he defined this almost strong conversion sequence spaces looks like this way. And the boundary sequences, the limit access to form them for some time.
The most powerful tool for finding of differential equations. Although regroup analysis was not fully appreciated by the mathematical community during and after these steps, it revived during the middle of the last century due to the efforts of Russian mathematicians that is Elvin Ovsyannikov and G. Brikov of USA. In the last 6 decades, there have been considerable developments in regroup methods for the differential equation, and it can be seen by the number of books devoted
by dark matter. So let me explain the word cosmology first, and then I will pass connect my information from cosmology to the general relativity, and then to the recent advancement in mathematics, and then to the cosmology of principle, and dark energy, and then dark matter. So it may take I think 2 to 3 minutes about this. So what cosmology is actually the large-scale properties of the universe as a whole. It includes the scientific method to study the origin, evolution, and ultimate fate of the universe. It involves the formation of theories and hypotheses that would make some predictions about a phenomena that can be tested observationally. Depending upon the outcomes of these observations, what we expect from, our theories can be eradicated, can be abundant, and can be modified or extended to accommodate the data. The most prevailing theory in our study about the universe is the Big Bang theory. It laid on 2 theoretical assumptions. Number 1 is general relativity, and number 2 is cosmological principle. So what is general relativity? It is the theory that was presented by Albert Einstein in 1915. He described this theory with the help of an equation which is perhaps 1 inch long, and it describes 4x4 matrix depending upon what kind of manifold we are taking. And then, what is cosmological principle? Whenever the general relativity was presented, everybody was trying to apply the new gravitational dynamics on the universe as a whole. At that time, there was a need of assumption. What is the assumption that we need to take in order to handle this universe? So, if you ever view the content of the universe with a pure vision, you see that it is distributed same everywhere in every direction. That the universe is homogeneous and isotropic, and this is what we call as cosmological principle. Okay, so recent advancement in cosmology describe that our whole energy distribution is distributed into 3 different parts: 69%, 26%, and 5%. 69% is what is described over here, dark matter, and 26 is dark energy. I will use the equation for dark energy in my calculations, and the rest is 5% in which we are all living and we can see everything, which is including that part. So what is dark matter? It accounts for the large part of the total mass of the universe as a whole. It neither emits nor absorbs any kind of radiations. We cannot say it, but its interaction or its existence can be seen with the help of gravitational attraction on the visible matter. We call this to be a dark matter, and this dark matter has some properties. Number 1 is it is particle nature. That this candidate includes weakly interacting massive particles and other heavy, slowly moving particles. That is the first property of the dark matter. And the next property is small scale issues. It has some small scale issues, because whenever an astronomer observation was taken at small scales and at the arena where the dark matter is, there are some issues that need to be addressed, and that is gravitational collapse. This whole dark matter relies on gravitational collapse to form structures, because there is a phenomena that is happening in the universe because of which new objects are formed, and this phenomena came into being because of the gravitational collapse, and because this clumps of dark matter, halos and galaxy structures came into being. So this is all what I can say about the dark matter. What is its role in cosmic structure and its evolution? Dark matter primarily interacts through gravity, exerting on gravitation pull on visible matter, as I stated earlier. And next is formation of cosmic structures, because it draws our attention toward the formation of cosmic structures, and after all, it will give some formation of cosmic web. This web is in the universe, in which filaments are there, in which voids are there, and in which many other things are there, and they are being distributed over the whole universe like a web. So this web came into being because of the dark matter, and there are gravitational lensing. Whenever there is an object and light passing from that one, it will be deflected, and all such phenomena can be called this to be very interesting because of the dark matter. Now, what is the question is, what makes a dark matter to be fuzzy? This is really very interesting. Let me explain this fuzzy. The concept of this fuzzy method predicts distinct observation consequences such as oscillations in the energy density, density profiles of the galaxies, and specific patterns in gravitational lensing. Whenever there is a phenomenon of gravitational lensing, there are some galaxies over there, and you can see some oscillations in the density profile of that one, and this happens because of the fuzzy dark matter. So what makes me to think in this direction? What makes me to think to develop or to construct the black holes in the fuzzy dark matter is because of the working of Ernesto. Ernesto is a person who gave a very good formula or mathematical expressions that can be used to detect fuzzy dark matter black holes. And this is a theoretical model. It has some restrictions that it must be non-negative and finite, and it should be smoothly decreasing function that approaches to zero at large radii, and certain movements associated with the rho density such as gravitational potential, then total mass, effect radii of the system, they should be finite. Whenever I use the formula of Ernesto density profile, then the final mass of the black hole, final radii of the black hole, and other gravitational potentials that are responsible for making the black hole to exist, it should be finite. And the descriptive function must not have jump discontinuity. And all of you may be familiar about jumps discontinuity that are very good topic in real analysis. So this is the mathematical form of the Ernesto density profile. It looks to be very beautiful because this is a mathematics. So one can apply this formula in the cosmic mathematics and get a very fruitful results. For example, here we have rho f, density of the sphere containing the total mass, and we have beta, that is Ernesto dense index, and then we have this r minus 2, and this is the radius of the sphere having special dimensions. So in the context of dark matter halos, now corresponding to each value of beta, I have different objects. I can have a dark matter black hole, I have a fuzzy dark matter black holes, I have fuzzy droplets, I have fuzzy cosmic webs, and I have even fuzzy halos, depending upon this formula and all the decisions that are used in this formula. Now the scale length according to this has been found to be here. I am going to describe the results of my research article here. So center density according to this has been found to be here. Now this is the equation that is found by solving the previous equation simultaneously. I found this to be equation number 5, and you can see that there are few things over here. One is H, scale factor, other is beta, Ernesto index, and next is rho naught, this is the density. So these three things are making a triplet. Depending upon these three, I have different varieties of cosmological objects. For example, if I take beta within this interval, then we have a dark matter halos with masses in the range of dwarf to clusters. Okay? And if I took beta to approximately equal to 4.35, it means if I take this value in my analysis, then it has been shown in the literature that it describes actually the cluster size halos. Okay? And if I take beta to be equal or something equal to 3.33, that describes massive halos for the millennium simulation. Okay? So these are the beautiful applications of my mathematics in our cosmic history. So the total mass that I found to be here, and if I use u to be parameter r by 4 to the raised power 1 by beta, then I found the mass of the black hole here, and with the gamma of 3 beta, this is a gamma function. With the final form, the energy density is What we need to do? Just we need to take this research article, we need to deal with the mathematics, and then I need to apply this mathematics to the problems, and then I see that they are presenting a real fuzzy dark matter black hole. And then Bustling formulated black hole simulation by considering some particular gravitational model. They made an attempt to discover the interior properties of black hole-like structure. And then they found a core cusp problem associated with the core dark matter. Core dark matter, but we call it to be just like the dark matter, but it has only particle-like properties. And Ludo showed that spherically, every density profile of dark matter halos can be accurately described by inertial density function. It means that function has a direct contact with DMH, dark matter halos. What my research article is, I would like to present a dark matter halos which is a resonant Nordstrom black hole, or I can say the charged black hole. For this, I would like to take this density tensor which is given over here, and according to this, the Tolman-Oppenheimer-Volkov equation, what I call this to be a hydrostatic equilibrium equation. I found this to be here for my analysis, and where I have used this identity in my analysis. And this is anisotropic in nature, and according to which I take the Nernst density profile and I model my mass in terms of equation number 13. Now we will use the DC equation of state rho u minus PR. This equation clearly describes the dark energy contribution in our fuzzy dark matter black holes for this radial and tangential pressure that are contributing in the development of my stellar structure is going to be here. What I show here, you can see this is here is the pressure of a black hole, and this is the radius of the black hole, or a special ratio of the radius of the black hole. One can see that this is minimum, and here the radius is 0. It means whenever I move inside the black hole, I found the minimal contribution of radial pressure. When I move out from the black hole, I found the maximum pressure because of the fuzzy dark matter. And here I can see the same kind of behavior because of the fuzzy dark matter profile. Now, this is the temporal component of the relativistic gravitational potential. Yes, potential is very important. And if it is relativistic, then it is beautiful. And if it is temporal, then it's very beautiful, because it is trying to contribute the formation of a black hole. So here is some expression I found with the help of some calculations, and after some manipulations I found this to be here, and this is a graphical representation that clearly shows that our fuzzy black hole is realistic, and it is describing really a realistic object. Okay. So next I will describe the diffuse self-gravitating droplet. For example, I found a graphical representation. This is that is a red color that is describing omega equal to 0.7 and other is omega equal to 0.94. These options are not arbitrarily chosen. Rather, they have been supported with the help of observations and other, and they are describing different streams of black holes at a specific arena of space-time. Now, the value of H1 scalar, as it is working, there are many people work on that in this, even in the faculty of University of Education, many people work on that, the H1 scalar, and it is contributing towards the existence of matter on the space-time. And this is, you can see that R sphere is trying to produce a singularity. In our case, when I used my data net, I found singularity-free Riemann scalar at a specific area, a specific limit. This clearly shows that the fuzzy dark matter black hole is realistic. So what are my conclusions? The first thing that I would like to include here, there is a possible connection between dark matter and black hole physics by considering inertial density profile. I am also endorsing that the profile which was presented by Nastro is really unrealistic if I study the dark matter black hole, fuzzy dark matter black hole. Different black hole solutions by making certain choices for underlying equational state are possible. Yes, one can have a different black hole solution corresponding to each different value of equational state parameter. Now, under dark energy interactions, yes, there is a dark energy because there is something which is counteracting gravity. There is something which is trying to pull everything away from each other, and that is a dark energy. Under this background, it is possible to conduct a self-gravitation droplet, and if there is no horizon, we can call this